Good morning, everyone. So, am I audible?
Yes.
Okay. So, I welcome you all in the first session for today. And our first speakers will be Mr. Rene Villela from the Institute for Molecular Sciences, Japan, and Ms. Shweta from IIT Delhi. The title of the talk is Towards Quantum Simulation and Computation of Properties of Atomic Systems Using Cold Atoms. So we'll be taking the questions at the end of the chat, at the end of the talk, and you can put your questions in the chat. Start now.
Okay, can you see my screen? Can you hear my voice?
Yes.
Okay, good. So good morning, good afternoon, whatever whatever it applies to you. I would first like to thank the organizers for holding this great event, and also for the opportunity of giving us this chance to present our most recent project, which is titled Towards Quantum Simulation and Computation of Properties of Atomic Systems Using Cold Atoms. So there are many people involved in this project. Dr. Prasanna, myself, Shweta, and Professor Das, we have been involved in VQE related calculations, which is a concept that I'm going to introduce later on in the talk. And also all of us have been in some extent involving cold atom theory and experiments, which is the platform we will be considering to pursue this project. So let me start with some motivation, and that, as many of you know, quantum computing we expect many things from quantum computers in the upcoming years. And in theory, quantum computers promise exponential speed up in tasks like factoring big numbers, which is directly related to cybersecurity mostly, and like the case we are considering now, simulating quantum systems. So we want to understand quantum dynamics using the power of quantum dynamics itself. However, given the current state of quantum hardware, we have several issues, mainly noise and errors, and also limitations in the number of qubits, which is the fundamental quantum information processing unit that we have prevented us from exploiting the theoretical virtues of quantum computers. So if we want to still take advantage of the power of current quantum computers while not being affected by their many drawbacks, we have to be clever, and we cannot take a direct approach. We need to make some workarounds to make the best use of what is commonly referred to as noisy intermediate scale quantum hardware, NISQ for short, which is characterized, like I was mentioning, by the limited number of qubits and errors in the gates, which are the quantum operations on the qubits that prevents reliable results when we have many operations, and also limited interaction between the qubits themselves. So whatever approach we consider, we have to take these things into consideration. Also, let me briefly talk about the quantum many-body theory of atoms and molecules, which is what we're going to be using to calculate the atomic properties that we want. So in short, the quantum many-body theory of atoms and molecules is nothing but the application of quantum mechanical concepts to the study of atoms and molecules. So as many of you know, the Schrödinger equation is not exactly solvable for most real systems. So we try to find approximate solutions for whatever system we are considering. And for atomic and molecular systems, the most common starting point for these calculations is the Hartree-Fock theory, where the Hartree-Fock wave function is approximated by treating the influence of other electrons. So instead of considering the single electron-electron interactions, we consider an electron to be immersed in a mean field potential, which is generated by the cloud of the other electrons. So this is an approximation that works to some extent to have a general idea of what is happening. However, for most systems, electron correlation or the electron-electron interactions becomes really important. So we cannot really rely on the Hartree-Fock theory. And therefore, we need what is usually known as beyond Hartree-Fock theories or methods. Some examples of these beyond Hartree-Fock methods are the configuration interaction method and the coupled cluster method. Both of these methods are based on, okay, we start from the Hartree-Fock state and we consider excitations of this state. So to virtual higher order orbitals. So both of these methods are based on that idea. They are parameterized in different ways and they capture different processes, but they are based on the excitations of the Hartree-Fock theory. And I'm going to discuss a bit more about the coupled cluster method later, which is something that we are considering for current purpose. But the drawback is that these methods get highly resource expensive for larger systems. So if we are considering an atom with many electrons or a big molecule, even with the most powerful supercomputers, we cannot really aim to calculate properties for these systems because it takes too long. We require too much computational power. So it seems natural to try to apply the quantum computing power to solve these kind of problems. But how can we make use of the power of quantum computing for this application? So first, let me talk about the idea of variational quantum algorithms. Like I mentioned in the beginning, the current quantum hardware is limited by several sources of noise and limited number of qubits. So we consider an optimization-based approach that addresses the constraints that current quantum hardware has. And by this, I mean that we will use classical optimization instead of using a purely quantum routine so that the circuit depth is kept shallower. So on a quantum processor, we will have strictly the necessary operations. Operations that we can do efficiently and on a classical processor, we will do them classically and keep the operations on the quantum processing unit to a bare minimum, just what we want to do. And it's recently been shown that VQA-based quantum computing is universal. So it is worth considering this kind of approach, and not only for atomic and molecular calculations, but this is a very general approach that can be applied for many types of problems. In general, these VQAs are based on the idea of defining a cost function, C of theta in this case, which is a function of an initial state, phi, an observable or an operator that we want to compute, O, and a set of unitary operations, the unitary gates, parameterized by these parameters theta. And the conditions that this cost function need to satisfy are that the solution, theta star, gives the minimum value of the cost function, and also that smaller values of the cost function imply a better solution. And when we use this general approach to calculate, well, if we want to calculate molecular and atomic properties, the best place to start is just computing the ground state energy of atoms is a good starting point. So when we apply this technique for the calculation of a ground state energy, we are talking about the variational quantum eigensolver technique, which is usually aimed at finding ground state energies of a Hamiltonian. And in this case, our cost function is directly the ground state energy of the system, which is defined by this expectation value of the Hamiltonian, where the wave function is given in terms of the unitary gates parameterized by the parameters theta. And the initial state is the Fermi vacuum, which is nothing but the Hartree-Fock state itself. So we start with the Hartree-Fock theory, and then by applying unitary transformations, we create a better state to calculate the expectation value of the Hamiltonian and obtain the ground state energy using that procedure. And also the Rayleigh-Ritz variational principle ensures that the minimum of the cost function will be the solution. So all this is powered by the variational principle in quantum mechanics. So since we're considering operations on a quantum computer, we must keep in mind that these operations need to be unitary. And an atomic or molecular Hamiltonian is not unitary per se, but we can easily transform it into a unitary form. So we start with a Hamiltonian, then we can express this in second quantized form using creation and annihilation operators. And we need to express these operators so that they are unitary. And we can use several types of mappings or transformations, among which we have the famous Jordan-Wigner transformation or the Bravi-Kitaev transformation. But the point is that we can express the products of creation and annihilation operators as tensor products of Pauli matrices. In this case, P alpha for short. This is usually called a Pauli string. So it's nothing but tensor products of Pauli matrices, including the identity matrix is also included in this set of unitary operators. So in this way, we can easily express the Hamiltonian in terms of unitary operations to be employed in a quantum computing routine. And here we have a schematic depiction of the variational quantum eigensolver so that I can better explain how all this works. So we start with our set of qubits in a quantum processing unit. We calculate the Hartree-Fock state, which is our starting point. Then we decide a set of unitary operations that we want to apply on the Hartree-Fock state and give it as initial set of parameters, theta input in this case, and calculate an initial value for this parametrization. Then also in the quantum processing unit, we calculate the expectation value of the Hamiltonian, which gives us the energy. We use these values and input for a classical optimizer, which is going to update the set of parameters. Then this updated set of parameters is going to be the new input for our unitary operations. And this is going to be a cycle until we reach a desired level of accuracy, until we reach the minimum of the function ideally, and we get a solution for our problem with a final set of parameters that will give the minimum of our cost function, which will be the solution. And I haven't talked yet about what kind of operations can we consider. So this is what I'm going to consider next. So if we want to calculate ground state energies of atoms and molecules, the most reasonable way to proceed is to use a already physics-inspired technique. In this case, it's called the unitary coupled cluster, UCC-SD for short. This S and D mean single and double excitations. Like I was mentioning in the beginning, the coupled cluster method is related to excitations of the Hartree-Fock state. So for short, we are only going to consider single and double excitations, which give a reasonably correct result for smaller systems. We can, of course, consider more, but this is a good starting point. And the unitary coupled cluster is just a reparametrization of the coupled cluster method to make it unitary, because the coupled cluster method itself, the operators involved are not unitary and therefore cannot be used for quantum computing purposes, but it can be easily parameterized again to make it unitary. So the original coupled cluster operator is just e to the t. This t is related to the excitation probabilities of the Hamilton of the Hartree-Fock state. And by redefining the operator as e to the t minus t dagger, it becomes unitary. And the good thing is that it keeps the right physics from the coupled cluster method, because although we are somehow changing the operator, it is still based on the idea of excitations of the Hartree-Fock state. So although the parameters are going to be different, it keeps the same idea of excitation. So it's physically similar. And by parameterizing it in this way, we get something more for free, that the expectation value of the energy using such a state satisfies the operational principle. However, even if we only consider single and double excitations, the unitary coupled cluster circuit is too deep. It's too deep for current quantum hardware. So it sounds nice. It sounds nice that it's physics motivated. It is very precise for smaller systems and giving comparable results to the full configuration interaction method, which gives the best value that one can obtain for a given basis set. But however, the circuit is very deep even for small systems. So instead, we consider a more general heuristic approach known as hardware efficient ansatz. This circuit is shallower, is flexible, cannot be applied for a variety of problems, not only atomic and molecular problems. Is a very general technique, but its precision is unclear because, I mean, it has no physical motivation. It's just a very general technique that seems reasonable. And since our goal here is to finally implement these techniques on real quantum hardware, we are not going to focus on the unitary coupled cluster now. We are going to focus on the hardware efficient ansatz because the circuit depth is shallower. So for now, we need to use this technique if we want to use this idea on current quantum hardware. So the concrete steps for the implementation of this routine are the following. We begin with an initial state, the Hartree-Fock state in this case. The idea behind the hardware efficient ansatz is that by successfully applying a set of single qubit rotations and entanglement and repeating this in layers, so rotation, entanglement, if we do this long enough, then our final state will overlap sufficiently with any arbitrary state. This is the idea behind the hardware efficient ansatz. So after we prepare the Hartree-Fock state, we rotate the qubits to a given superposition, and these rotation angles become the parameters in this case. And then all the qubits are entangled using 2 qubit gates. Can be entangled in other ways, but for now, the easiest way to do experimental is just using 2 qubit gates. And like I said, this is a type of ansatz that comes in layers. So we construct one layer, and then we repeat the layers as much as we need to get a good final state. And here in the figure, you see an example of such an ansatz, where here we have the single qubit rotations, and then we have an entanglement block, and then we have more rotations, and we would have to repeat this over and over again. And now I'm going to discuss the problem that we are considering. So we have decided to consider the beryllium atom, which is a 4-electron atom, closed shell. It has very good properties, so it's a very good place to start. Our choice of basis is the STO 3G minimal basis. Again, just making our life simple to explore how this technique behaves for simple scenarios, then we can proceed and have much more complicated scenarios. And in this case, we have 10 spin orbitals, that is 10 qubits for calculation. While in UCC, the parameters to be optimized are related to the excitation probabilities, there is no such physical equivalent in the hardware efficient ansatz. The rotation angles are just that, they don't really carry any physical meaning. And here in this table, for your reference, you see the ground state energy of the beryllium atom for different techniques. So this is the unitary coupled cluster singles and doubles using a simulated VQE procedure and the Jordan-Wigner transformation and the state vector backend. This state vector backend just means that we are simulating ideal quantum computing conditions. We are not artificially introducing noise. So this is supposed to mimic a perfect quantum computer. We also have tried the UCC-SD on a classical computer without applying the VQE technique. We have the energy of the initial state, the Hartree-Fock state, the full configuration interaction, which is our main benchmark. This is the goal. This is the best result that we can get using the STO3G basis, and the coupled cluster singles and doubles, just for reference. And just for comparison, here you see how the situation would change if we are considering between the two ansatz. So the number of qubits is the same in both cases. However, for the unitary coupled cluster, we will have to consider 54 parameters to be optimized. For this hardware efficient ansatz, it's just 40. And the problem comes in the number of gates. So if we're considering the unitary coupled cluster circuit, for single excitations, we need more than 100 gates. And for double excitations, we need many, many, many more gates. While for one layer of this type of hardware efficient ansatz, so RY, RC, CX, we only need 49 gates, which is a reasonable number. However, as you will see in a moment, this hardware efficient ansatz appears to give results very close to or above the Hartree-Fock energy value, which is not great. It is not what we would hope for. But we believe that by finding a suitable ansatz, we can solve this issue. So the hardware efficient ansatz is a very general technique. There is no unique way in which you can define the layers. So this RY, RZ, CX is just one example of the rotations and entanglement that you can have. But as long as you have layers of rotations and entanglement, it still applies. So maybe we can use a better set of gates or a different type of entanglement. Maybe we think that this can improve the results, but for now, the results that we have obtained are the following. And we have tried a few different types of layers and also a few different types of entanglement. But what you can see here is the line in red, which is the hardware efficient ansatz. It seems to, okay, and here in the x-axis, you see the number of layers. So we have tried many layers, well, up to 20. That it goes up and down, but it doesn't seem to go below the Hartree-Fock energy, which is not what we would be hoping for. But in the near future, we'll be trying to solve this issue by using other types of ansatz and maybe considering better entanglement routines and so on. So now I'm going to give the microphone to Shweta, who is going to tell you how to implement these techniques on a cold atom-based quantum computer. So thank you.
Yeah, hi, I'll be sharing my screen now. It's visible, right?
Yes.
Yeah, okay. So, but I'll be discussing is the cold atom based quantum computing system, which will be we will be setting up in our lab at IIT Delhi under Professor Bodhaditya Santra. So I'll be giving an overview of how these circuits, which Rene was showing previously, they can be practically achieved. So first we have to set up a mode, that is a magneto-optical trap, which consists of which makes use of the concepts of Doppler cooling and magnetic confinement to trap the atom clouds in a tweezer, and then there will be the probabilistic loading of these single atoms in the optical tweezers, so we can make various operations on them. So there that's why we will be loading those atoms in those optical tweezers. And then those single atoms, they are not ideally loaded, like they are not in a configuration which we can use them to comply in our setup. So that's why we need the defect free array. So we will be rearranging those single atoms in a defect free array. So then this Professor Buckle's group, you can see they have shown that these 100 atoms in a defect free array, 105 atoms in this configuration, and 111 atoms respectively. So you can see that there is not a single defect in this 2D array. So like no a single position is open, vacant, or like this. So that's what we mean by defect free arrays. And then after that we will be implementing the gates which we require to complete a circuit. So how we can implement those gates using those neutral atoms. And after that there is the one thing left, that is the final state readout. So how we measure the states of the atom, like in which state they are present by using cameras and so this is the basic overview of the entire setup, how we can achieve those results and how we can implement those circuits in our experimental setup. So I'll be discussing some these things in a somewhat more detail in the next slides. So now here is an example of this RYRGCX sensors, which is a hardware efficient sensors, as Rene was discussing previously. So I have taken an example of a 4-qubit system, which is for the H2 molecule. And here you can see that there are this circuit is consisting of 4 gates, which are poly X gate, RY theta rotation gate, and RG theta rotation gate, and also an entangling gate C naught. So as you can see, like we have used only one layer of this hardware efficient answers here, so that to simplify our explanation, and so that we can expertly explain that how this is going to be applied. It is merely for the reducing our complications. So now this circuit, it was obtained using Qiskit simulation in Python, and now we will try to implement this circuit using cold atoms in our system. So now some basic building blocks are here. So these are the components of circuit they will be using in our atomic setup. So since Ry theta, this rotation gate around y axis, it can be decomposed further into rotations around x axis and z axis. These rotation gates, which is Rx minus pi by 2 rotation gate, and Rz theta, and then followed by Rx pi by 2 rotation. So it is merely to reduce the number gates which we'll be using in our setup. So that's for this Ry theta rotation gate. And now these are as you can see, we will be using further this Rx 3 pi by 2 gate in our circuit, because it will be implemented because of the simplification of Rx 2 pi gate and Rx minus pi by 2 gate. So it will simplify to this Rx 3 pi by 2 gate only. And then after that, this is Rx pi pulse. When it is combined with this Rx minus pi by 2 pulse, it will give us this will give us a resultant in Rx pi by 2 rotation. And also this poly X gate, it is merely a Rx pi pulse, this pi pulse given around this rotation around X axis in the Bloch sphere. And also this CNOT gate, as various esteemed speakers have spoken previously about in last 2 days about various applications, like how there are various methods by which we can implement also CNOT gate. So I have taken a form of that. So what we can do, this is the control atom, this is the target atom for the CNOT gate. So what we can do is we can apply 7 pi pulses in a manner such that we achieve the desired result for that CNOT gate. So first there will be a first pi pulse applied on around x-axis rotation gate, and it will be followed by these 5 pulses on the target atom, and again there will be a pi pulse applied on the control atom. So these are some building blocks which we will be considering in the construction of our main circuit. So I'll be discussing that further. So first, these are the single qubit gates, like how they can be implemented in our experimental setup. So single qubit gate, they can be implemented by rotation gates around various axes. So like RX gate, you may be familiar with it, like RX theta rotation gate. It can be written in this form, matrix form. Its decomposition is like this, and also RY theta gate is this, and RZ theta gate, it is shown by this matrix. So now how do we implement these rotation gates into our setup? So it can be implemented by using various lasers between some different levels of the atoms which we'll be using. We are going to be using cesium atoms in our lab. So now how do these atom laser interactions make these rotation gates? So these atom laser interactions, these are dependent on various factors. So first is the Rabi frequency of the laser, like it is dependent on the intensity and so, and also the detuning delta, which is the difference with the resonant level, like how off resonant is it, and also the relative phase between different laser pulses, and also like how much longer for a time tau we are applying that pulse field. So now these rotations by which are dependent on these various factors, these are introduced around these axes X, Y, and Z with angles which are given as this omega tau cos phi rotation along x axis, and omega tau sin phi along y, and delta tau around z axis. So now this example I have taken out from Professor Lukin's paper. So there they have shown the application of this Z5 gate. So a single atom, this phase gate, is implemented by applying some independent 809 nanometer laser, which is an off-resonant laser from the level scheme, and which induces a light shift of delta is equal to this amount, which is 25 megahertz on this for a time t, which results in an dynamical phase of phi is equal to delta t, and according to that phi resulting, the phase gate is introduced along z axis. So that's how these single qubit gates can be implemented using these rotation gates. And now, as in the last lectures you have also heard about Rydberg blockade and so on, so I will be discussing it briefly. So when a control atom, consider a control atom, it is going to a Rydberg level by some excitation, so it introduces some shift in the Rydberg level of the second atom, which is in the vicinity of its Rydberg blockade radius, such that when second atom is required to jump to that, which is the target atom, which is required to jump to that Rydberg level, it can't do it. It can't go to its Rydberg levels, such that it's blockaded from going to its Rydberg level. So that is the phenomena of Rydberg blockade. So it's this atom will have some Rydberg blockade radius along in the region of which no atom can further go to that atom's Rydberg level. So that blockade radius is given by this expression, where C6 is the van der Waals coefficient, and this Rydberg blockade, it is very useful in realizing the 2 qubit gates, as I will be explaining further, and also entangling the various qubits. So that's how helpful this Rydberg blockade phenomena is. And now coming to the 2-qubit gate implementation, as I showed in the circuit which we got from the Qiskit simulation, we were using the 2-qubit gate, that was CNOT gate. So how this CNOT gate can be implemented. So now this figure, it is showing the CNOT protocol. The pulses applied here, or in the order 1 to 7, are all pi pulses, and we also make use of the Rydberg blockade in the implementation of this CNOT gate here. So let's take the input states. Let's take that the both input states are in 0, 0 of the control and target atom. So when we take that the control atom, it is in 0 state. So when we apply the first pi pulse, that is on the this first pulse, it sends the control atom from the 0 state to the Rydberg state, and the atom will stay there until we apply some other pulse. And the target atom, it is also in the 0 states initially. So we again apply the pi pulse on the which is the second pulse on the target atom, but it will not send that atom with the 0 state to Rydberg state, because the control atom is already in its Rydberg state. So it will blockade. Rydberg blockade will come into picture here. So it will not send this atom to the Rydberg level, and so the target atom will remain in the 0 state only. And after that, the third pulse is applied, which sends the target atom from the 0 state to the 1 state, and it remains there. And after that, the fourth pulse should be ideally applied, but atom is since not in the Rydberg state, so it will not be applicable here. And so the atom is again in the 1 state, and when the fifth pulse is applied, the atom goes from the 1 state to the 0 state, and so the atom remains here. And sixth pulse, when it is applied, it will not have any effect, because it is bringing the atom down from the Rydberg to 0 state, but our atom is already in 0 state. So our target atom, it goes from 0 to 1 to 0 again. And after that, the seventh pulse, it is applied, which brings back our control atom from the Rydberg level to the 0 state. So our control atom again, it also comes from 0 to R and R to 0. So that's how the input, when the input state is 0, 0, it again transforms to 0, 0 state. Similarly, when the input states are 0, 1, 1, 0, and 1, 1, they transform to 0, 1 output, 1, 1, and 1, 0. As you can clearly see that when the control atom is 0, the target atom remains the same, like it remains in the same state. But when the input state is 1, the target atom, it flips its state from 0 to 1 and 1 to 0. So in this way, a CNOT gate, it can be implemented. So this was the implementation of 2-qubit gate. And now how can we implement this whole building blocks in the form of a circuit? So I'll be explaining the same circuit of the RY, RZ, and CX sensors, which I had taken an example of here, like implementing this poly X gate, RY theta gates, and RZ gates, and also these CNOT gates in the succession in a one layer. So yeah, so here you can see these are the 4 qubits, Q0, Q1, and Q2, Q2 and Q3. So the first atom, we need first an X gate, which is a poly X gate, and as explained, that X gate is a RX pi pulse. But when it after that, we also have to implement an RY gate, which will be basically broken down in the form of 3 gates: RX minus pi by 2 gate, RY theta naught, RZ theta naught, and RX pi by 2 pulse. So those RX pi and RX pi, minus pi by 2 combine to make a RX pi by 2 gate only. So it is the first gate in the Q0 qubit, that is the first qubit. And after that, here it is the second pulse for the Y gate, which is RZ theta naught gate, and also then RX pi by 2 pulse here. And after that, it is the this green gate, it is the RZ theta 4 gate, and this will be simultaneously seen in the other 3 qubits also. Like when we had to apply a X gate on the first qubit, the Q1 qubit should remain same. It must remain in the state Q1 only. So For that, we can do one thing, like we can apply a Rx 2 pi pulse, but when it again combines with the Rx minus pi by 2 pulse, it will give a Rx 3 pi by 2 pulse, Rx 3 pi by 2 gate. And these, as you can see, that Q0 and Q2, they will have the same initial states here. They will have these gates in succession, and also Q1 and Q3, they will also have the same gates applicable. And after that, after this block is over, we want to apply C0 gates in quick succession on Q0, Q1, where Q0 is the control, and then again C0 gate where Q1 is the control and Q2 qubit is the target, and after that again Q2 is the control and Q3 is the target. So the first pulse, which is the Rx pi, this pulse will be applied here, and after that in succession, these pulses, 5 pulses, which will be applied on the Q1 qubit, which are the Rx pi gates only. And after that, here we must apply Rx pi, but when it combines with the minus pi by 2 pulse around for the Ry gate, it will give us again a Rx pi by 2 gate. So that's how these contribute to give us a Cx gate, which is the C0 gate. Again, the second gate is applicable also like that. And again, the third C0 gate is obtained here. And after that, we have to apply this Ry gate, which is decomposed in the form of Rx minus pi by 2, Rz theta 8 and Rx pi by 2. And again, after that, it is the Rz theta 12 gate. So that's how we can obtain this circuit fully using these pulses, these theta pulses around various axes, and we can also obtain in this way these 2 qubit gates. And now I'll be showing just for idea purposes, like how the pulses can be applied. This is a pulse scheme for by black. In the black color, we can see the Raman pulses which will be applied, and for the in the purple shade, we can see the Rydberg pulses which will be applied for various times. And these first pulses, these are denoting the pi by 2 pulses. And second, these are denoting the pi pulses, and third, these are the 3 pi by 2 pulses, and these pulses, purple pulses, these are the various thetas which will be applied. So here, that is that for the circuit implementation. And now we have to also consider the sources of error. So sources of errors in which when we do our experiments, we also we want to consider them such that there are some we can improve them, and there are some realistic results, like how we obtain them. So they can be further classified into 3 classes, which are decoherence errors, gate errors, and step preparation and measurements, which are spam errors. So now, what are the decoherence errors? So they can be classified further into 2 classes, which are longitudinal coherence time, which is T1, and dephasing time T2, where T1, it is this time it measures the loss of energy from the system, like how it decays this state. And also the dephasing time T2, it is a time interval after which the resonance frequency of qubit that becomes unrecognizable, like it is not the frequency which we have initially given. So these are the decoherence errors, however qubit evolves. And again, after that, these are the gate errors, which are single qubit errors and 2 qubit errors. So as Professor Safman in his lecture also mentioned, like fidelities which have been achieved for till now for the single qubit error, these are for global gates, the fidelity achieved is 0.9998. And for the local gates, the fidelity achieved is 0.993. And for 2 qubit errors, the fidelity achieved, it is 0.955. And also the state preparation and measurement errors also come into picture. So when we take them into our consideration, so it is the fidelity which has been achieved till now. So for the preparation of Bell states using controlled phase gate, the fidelity measured is to be 0.898. So thank you. Here I will like to end my presentation.
So thank you, Mr. Rene and Shweta, for your talk. And now we will be taking up the questions. So first question is for Mr. Rene, I think. So, Mr. Rene, can you hear me?
Yes, I can hear you.
Okay, so the question is, what do you mean by a circuit being deep or shallow?
Okay, by these I mean just basically the number of gates involved in your circuits. And if you have many gates, then your circuit is said to be deep. And if not, then it is shallow. And the number of gates is directly related with the error of your outcome of your measurement. So we wish to have shallower deep circuits, or which just means that we want to have as few gates as possible in this case.
Okay, thank you. So are there any more questions? I would like to ask one question. So when you show the propagation, or you can say the estimation of errors, when you use a different number of layers, can you just go back to that slide?
Okay, okay. Can you see my slides?
Yeah.
Okay. Okay, here.
Yeah. Yeah. So when you talk about these different layers, like when
Yes.
you vary the number of layers, so is there a way to not just calculate the difference in the energies, but also the overlap of the wave functions from the two methods, like fidelity, susceptibility?
Yes, in theory, if the more layers you have, the better your overlap with your desired state will be, and it's supposed to improve your energy expectation value. But in real hardware, of course, increasing the number of layers would have the drawback of making your circuit depth deeper. In this case, it's just the simulated quantum circuit, so we are not considering errors. So it shouldn't affect in this case. So for a simulated scenario, it is a way to quantify the overlap of your state with your goals. Yes.
Okay, thank you. So I think now we can move on to the next session. So may I request Professor Vasan to proceed to the next session.
Thank you, Professor Singh. I think still we have a time, so I can wait another 2-3 minutes. So there is a small interval here. We can meet again at 12:25 for next talk.
Hey man,
Hi. You are here, yeah.
Yeah.
So, Ajay, shall we? I mean, we have about 10 more minutes.
Yeah, I mentioned 12:25 we'll meet.
Okay, fine.
So I will introduce around
We'll start at
12:25.
12:25. Okay.
Yeah, yeah.
Yeah, if you guys make me host and then I can start. Uma. Hi Ajay, how are you?
Yeah, fine.
Fine. So what is
Yeah.
this background? It's
No, actually, this should come. We are celebrating our 175 year here in IT Roorkee.
This is live on, it is streaming live on YouTube. Maybe we can stop that now.
Okay, sorry. Yeah, sorry.
okay.